Hello guys. So today we continue to discuss topics related to image formation. Now, as you remember, last lecture we discussed the formation of images in spherical, like by spherical mirrors, and today we are going to consider formation of images by thin lenses. But initially, will be necessary to consider just formation of image by refraction, where we will have some interface between two transparent mediums with different index of refractions. So it will be considered in the case of some curvature of this interface, and in the case of a flat interface. Then we will proceed further and apply some derived equations for these systems to lenses, so which actually are represented by two surfaces with different curvatures. They could be like the same, but can be also different, and some refractive index which defines properties of the material from which this lens is made. Okay, so let us first maybe share the screen, then we will change the camera. And I share the screen. Okay, so let us consider first interface of two conductive transparent mediums, so with refractive indexes n1 and n2. So for instance, we have this object, and then we want to know get some information about the position of the image of this object as a function of position of the object and like curvature of this interface, and also refractive index of both of mediums which form this interface. So we know that from the law of refraction, we have such dependence n1 times sinus theta 1, which is medium from where the light is traveling towards the interface, and theta 1 is angle of incidence, and it is equal to n2 times sinus theta 2, where n2 is the refractive index of the material where in which the light is refracted, and theta 2 is angle of refraction. So assuming that angles theta 1 and theta 2 are very small, then we can write that sinus theta is with some approximation equal to theta. And then we can rewrite this law of refraction as n1 times theta 1 equals to n2 times theta 2. So now let us take a look again at this slide on the bottom image. So we have some ray which is approaching the interface between two transparent mediums from the right side. Then it is refracted and reaches the point where the image is located of this object. So here we can consider some triangulars. For instance, OP So this triangles, wait, we need to get information about angles alpha, beta, and gamma. So taking into account the fact that the exterior angle of any triangular equals the sum of the two opposite interior angles of this triangular, we can write the relationship between theta 1, theta 2, and these three angles, alpha, beta, and gamma. So let us do it right now. Sharing. So based on that image, those triangulars, we can write that theta, it's not theta, theta 1 is equal to alpha plus beta, and beta is equal to theta 2 plus gamma. So based on these relationships between these angles, we can eliminate theta 1 and theta 2 from previous equation, like simplified equation for the law of refraction, and we will get the following: n1 times alpha plus n2 n1 times alpha plus n2 times gamma is equal to n2 minus n1 times beta. So I remind you, n1 and n2 are values for the refractive index of different mediums. So now we can assume that since theta 1 and theta 2 are also small, then tangents alpha, these angles alpha, gamma, and beta should also be quite small. So we can write that tangent alpha is equal in first approximation to alpha, and that is equal to d divided by p. If we start sharing this screen again, so you can see the image. So p, again, it's distance, as we discussed earlier, from the object to the interface with some curvature. Q is the distance from the this interface to the image, and d is this distance from the principal optical axis, and the point P, which we consider like point where the refraction is happening. So based on these right angle triangulars, we can express alpha, beta, and gamma in that way which we are currently doing. Let's come back to our slide. Then will be tangent beta, first approximation equal to beta, and that will be equal to d over r. R is the curvature of the interface, radius of this curvature, and tangent gamma is in first approximation equals to gamma, and that is d over q. So taking into account these equations, the previous formula can be rewritten in a different form, more practical one, with which we are going to work during this lecture. So this is n1 divided by p, distance from the object to the curvature, plus n2 divided by q. Q is the distance from the curvature of the interface, from the interface to the image of the object, and that is equal to n2 minus n1 divided by r. So this is an important equation which quantitatively describes the image formation by refraction and gives us the relationship between the position of the object P, the position of the image Q, and properties of the interface between two transparent mediums with index of refraction n1 and n2 respectively, and the radius of the curvature of this interface equals to r. So we also need for these purposes to consider signs of like positive or negative values for these parameters. And for instance, for parameter P, which is object location, it should be positive if object is in front of the surface, real object, or object is in the back of the surface, virtual object, which is applied in the case of a magnifying glass. Then image location Q will be positive if image is in the back of the surface. This interface means a real image, or negative if the image is virtual. The same for image height. It is positive if it's upright and negative if it's inverted. I mean the same as for the signs when we deal with these parameters in case of spherical mirrors. And for radius of this curvature, if the center of the curvature is in the back of the surface, then this radius is positive, and opposite if this center of the curvature is in front of the surface. So actually depends either on orientation of this curvature or from which side this beam is traveling. So it definitely determined by the relative orientation of incident beam and curvature of this interface between two materials. Okay, so now we can consider some specific case, which is image by refraction at a flat surface. So in this case, you see we have some object in one medium, some rays coming out because of difference in the refractive index of these two mediums. These rays are diverge, and if we extend this diverged refracted rays towards the interception, these dashed lines, they will give us the image. Since the refracted rays do not go through the image and only appear to diverge from the location of this image is virtual, and it should be mentioned that all images formed by refraction at a flat surface, flat interface between two different transparent mediums, will be always virtual. So let us sorry, somehow it didn't work and you didn't see the image. Okay, so this is what I was talking about. So here is the object in some medium, and there is a flat interface. So if we extrapolate this refracted rays from the second medium towards the interception, here will be the image, and this image will be virtual. So that's why each flat interface forms virtual image, and its location in front of the like right side from the object or left side from the object will be defined by the ratio of refractive indexes. So let us show this quantitatively. So if we have a flat interface, then R, the radius of the curvature, approaches to infinity, and then we can write N1 divided by P is equal to minus N2 divided by Q. So because one, like something divided by R, which approaches infinity, will just go to 0. From here, we get Q, which is the distance from the flat interface between two transparent mediums to the image, will be equal to minus N2 divided by N1 times P. So if P is positive, then this Q will be negative, means that the image will be located on the like in front of the interface from the same side as the object, and that is the sign of the virtual image. So its exact location will be defined, as I mentioned, in front of or behind the object, will be defined by this ratio of refractive indexes. But for this particular configuration, we will always get imaginary, like this virtual image. Now let us proceed further and discuss the formation of images by thin lenses. So it's also formation by refraction, but lenses are a bit more complicated because we have two curvatures. So let me share the screen. So here we have an image of some lens. We have radius R1 describes curvature of the first interface. Radius R2 describes curvature of the second interface. So here we have the object. Then we need to consider first image formed by the first surface of this lens. Then we need to consider the image of the, in order to take this like, effect of first interface when we want to get the image formed by the lens. So it's actually image formed by two interfaces, like let's say air, glass, and then glass, air again. So in order to take this into account, we first find the image formed by the first surface, and then consider image formed by the first surface as an object for the to build the image formed by the second surface. Once we did like that, we eventually will get the image formed by the lens, taking into account the effect of both interfaces, like image of this real object. Okay, so let us switch to the slide where we can write, and now we assume that N1 is unity, so it's air. So we have air, glass, glass, air. The surface 1 is interface between air and glass. Surface 2 is interface between glass and air. And now we can apply this general equation for the image by refraction. Instead of N1, we just put unity divided by P. This is distance from the real object to the first interface, first surface of the lens, plus N. So we assume that N2 is equal to N. Just N is refractive index, let's say, of glass, the material of the lens, divided by Q1. It's the distance from the first interface to the image of this object formed by the first interface. And this is equal to N2 minus N1. It's N minus unity divided by R1, because we are dealing with the first interface of the lens. Now for the second, we can write the following. So now we have N 1 is equal to n, and because beam is already inside the lens, inside the material of the lens, and n2 will be air because it goes out from the lens to air again, back to the air. Then we have this equation for the image formation by refraction for the second surface. And P divided by P2, which is distance from the image of the object formed by the first surface, plus 1 over Q2, it's the distance from the second surface to the final image we are interested in, formed by two surfaces of the lens, equal to 1 minus n divided by R2. So now we need mathematically show that we consider image of the object formed by the first surface as the object for the calculation of image of the second surface. And if we come back to the image, like this slide with the image, we can see that P2, so this distance from the image of the first surface to the second surface, will be equal to Q1, like minus Q1 plus T. So minus Q1 because in this particular case, we see that Q1 is negative because it is the image is imaginary, like the virtual image, and it is located in front of the first interface. So that's why we can write. Let's come back to the slide and go to another slide. That P2 is equal to minus Q1 plus T. And plus T is the thickness of the lens, which is the distance between first surface of the lens to the second surface of the lens. So if we neglect with the thickness of the lens, because we are working now in the approximation of a thin lens, so T is negligibly small in comparison to the distance Q1 and P2, then we can write that P2 is equal to minus Q1. And now we can write the equation for the second surface, taking this into account. So we can write that minus n divided by Q1. So instead of P2, it was in denominator P2, we put minus Q1. Then plus 1 over Q2. This will be equal to 1 minus n over R2. So now, if we add together the equation for the first surface and the modified equation for the second surface, we will get such a combined equation. And also we can neglect with the subscript 1 Q1 Q2 and P1 P2, because these distances are considered to be equal to each other, because the thickness of the lens is considered to be negligibly small in comparison to these distances. So we consider an image formation in a thin lens. So in this case, we will get 1 over P plus 1 over Q equal to n minus 1 times 1 over R1 minus 1 over R2. So this is important equation because it gives us in details relationship between the position of the object and position of the image, refractive index of the material of the lens, assuming that the environment where this lens is located is air, and radius of curvatures of both first and second surfaces of the lens. Now we can consider one special case when P approaches to infinity, means that the object, the image of which we want to build, is located very far from the lens. Means that rays which are coming from this object are kind of parallel to the principal axis. In this case, the previous equation can be modified, and it will be 1 over Q. Q is the position of the image. It is written here as 1 over F equals to n minus 1 times 1 over R1 minus 1 over R2. So this F is the focal distance. We already know this parameter from as a characteristic of spherical mirrors. If rays, optical rays, are approaching the lens in parallel to the principal optical axis, then they will be focused in the focal point at the distance from the lens, which is equal to F, and that is focal distance. So now if we take into account that 1 over F is equal to the right side of this equation, we finally can write the equation of the lens, like thin lens, and it will be 1 over P plus 1 over Q is equal to 1 over F. So here we have the general form for the thin lens equation, which is technically the same as spherical mirror equation, and gives us the relationship between the position of the object, position of the image, formed by thin lens, and its one of its main parameter is focal distance. So by the way, this equation, which gives us the relationship between focal distance and parameters of the lens, is called lens maker's equation, because it gives the parameters of the material and radius of the curvatures, first and second surfaces of the lens, which are necessary in order to get some given required focal distance of this lens. So also the magnitude of the thin lens, the magnification of the thin lens is given as ratio of the image size to the object size, and is equal to minus q divided by p. Of course, since we operate with this lens equation in the same way as with spherical mirrors, or so we need to take into account the signs of these parameters. The rules are the same as rules for the image formed by refraction. P is positive if it is in front of the lens. Q is positive if it's from the other side of the lens, like behind the lens. And so on also is applied to the center position of the center of the curvatures of the first and second surfaces of the lens. Okay, so today this is pretty much everything what I wanted to tell you. Thank you very much for your attention. We discussed during this week introduced like nature of light and main concepts of ray optics. Then we discussed in details formation of images in the systems which are based on spherical mirrors, and also considered the formation of images by thin lenses. So for geometric or ray optics, we are pretty much done. Of course, there is some additional information you need to work with yourself with the textbook. In particular, I mentioned last lecture this total reflection, dispersion, like wavelength dependence of index of refraction. Also, what is related to the image formation by thin lenses. Please spend some time reading about image formation by a system of lenses, and also some most common optical instruments like microscope, telescope, what is their construction and principles of functioning. So with this we finish the ray optics, and then we will proceed further with the discussion of other effects, mostly with the wave nature of light. Also, I want to remind you that tomorrow we have the third midterm. Please be ready for that. be sure that you have secured internet connection. And there will be 8 problems, as you may know already. So please read all of them first and then start to solve problems from the easiest, which you know how to solve, and save enough time for thinking on solving problems which are more difficult. Don't spend all time on trying to solve a difficult problem and then get 0 points because you just didn't have time to solve simple problems which you knew how to solve. You just literally didn't have enough time to do that. Okay, thank you very much for attention. Have a good evening and good luck with the third midterm. Bye-bye.